Let's see what happens when congestion control has to switch from slow start to something more gentle. We'll switch from an exponential window increase rate to a linear rate. By the way, the phase that we increase the window at a linear rate is called congestion avoidance. Why congestion avoidance? We think that we've already aggressively approached optimal window size, and from there we'll be gentler and then start growing more slowly. But what is the limit? When do we switch from slow start to congestion avoidance? The limit is called the slow start threshold, which changes according to the following rule. If there is a segment loss event, the slow start threshold will equal half of the congestion window right before the loss. Let's look at an example. At first, the congestion window size equals 1. We run the slow start. There is no difference in the behavior of the TCP Reno and the TCP Tahoe until we reach the slow start threshold. Both of them are switching to congestion avoidance and are starting to change their window at linear rates until the phase when they see congestion. And the congestion window size just before the fall is equal to 12. What happens? The slow start threshold changes by half and will equal 6. In the case of TCP Tahoe, the congestion window size, the CWND, will be 1, and it will continue to grow to a value of 6. It will run slow start until the window size will be equal to 6, and from there, enter congestion avoidance. In contrast, TCP Reno is more optimistic. It will reduce its congestion window by half, and from there it will start the linear window size increase. This is the change you see here in black. Let's look at the finite state machine, which implements the congestion control inside TCP Reno. We have 3 states: slow start, congestion avoidance, and fast recovery. We talked about slow start. What do we need for it? We're increasing the window at an exponential rate to reach the optimal window size as fast as possible. What is the optimal window? When congestion doesn't happen, it's as big as possible, but there is no congestion. It's obvious that at a certain stage we will have to stop doing that, because the moment we grow too fast, we can pass the optimal window size. Because of that, at some point, we move to congestion avoidance. Also, there is another state called fast recovery. We said we don't always have to wait for a timeout, and we can use that time. Sometimes segments still come in. Only a tiny number of segments is lost. TCP is a pipeline protocol, and how acknowledgments are realized is by the receiver sending an acknowledgment with the following anticipated serial number. That means that if there are packets with larger serial numbers coming in, then it will simply send an expected serial number. From here, we can understand that segments can still pass, meaning there's no reason perhaps to even restart the window. We can use a duplicate ACK as an indication of packet loss. And the entire behavior is what we see as the fast retransmit. And how we change the size of the window, what's called fast recovery. Let's look at what happens in detail. We start everything in slow start at first. The congestion window equals 1 MSS. Slow start threshold, let's say 64 kilobyte. And there is a counter called dup ACK count, which equals 0. The moment a duplicate ACK comes in, we remain in the same state of slow start, but we sum the dup ACK count. Now, the moment that a new acknowledgement comes in, we need to increase the window. How do we increase it? After every ACK, we increase it by an MSS. That is why it grows exponentially. In dup ACK count, we begin at 0. We send the segment or more as we're allowed. We might need to later return to a slow start state. The next thing is that we're in a slow start and get duplicate acknowledgement 3 times. We'll have to switch to fast recovery. We'll talk about what we're doing in fast recovery later. If the congestion window is larger than the slow start threshold, we know that the slow start ended and we need to move to congestion avoidance. Let's talk about congestion avoidance. Now, if a new acknowledgement is received instantly, we are in congestion avoidance. We increase it at a linear rate. You can see the formula CWND equals CWND plus MSS plus MSS divided by CWND. That means that the growth of the congestion window is linear. Dup/Acc count is initialized at 0, and we send one segment or more as permitted. If the duplicate acknowledgement arrives, we increase the count Dup/Acc count by 1. If the amount of the duplicate acknowledgements equals 3, which is exactly what we saw, the slow start threshold will equal half the size of the congestion window. The new congestion window will be the slow start threshold plus 3, because it encapsulates the 3 acknowledgements. And we're starting to send the missing segments again. From congestion avoidance, we can also go back to slow start the moment there is a timeout. If a timeout happens, the slow start threshold will equal half the congestion window, and the congestion window will equal a single MSS Dup/Acc count initialized at 0, and we send the missing segments again. At that moment, we're done with congestion avoidance. Let's start talking about fast recovery. When do we move from congestion avoidance to fast recovery? As we've already mentioned, once there are 3 duplicate acts. The slow start threshold will be equal to half the congestion window. The congestion window will be equal to the slow start threshold plus 3. We resend the missing segments and then go into fast recovery. If a timeout happens, then we go back from fast recovery to a slow start state. We initialize the slow start threshold to half of the congestion window. The congestion window will equal 1, and Dup/Acc count initializes at 0. We send all the missing segments, as you can see. Once a new acknowledgement arrives while we're in fast recovery, then the congestion window will equal the slow start threshold, and the Dup/Acc count will initialize at 0.